All right, good morning again, everyone. Welcome back. Thank you for coming to AstriCon 2025, day 2. We are pleased, our third day, but we're numbering them 0, 1, and 2, of course. Talking a little bit now about cloud with Florian and Georg. I think this is an interesting conversation from a closed cloud to an open cloud. So very excited to see more open source support and running Asterisk in the cloud. Hand it off to Florian and Georg. Thank you.
Thank you. So glad to be here. Great audience. Yes, as Chris said, we'd like to take you on a journey how we transformed our business, how we moved from a proprietary cloud to an open source based one, and the roles of Asterisk and Kubernetes on this journey. A couple of words on our background. So we're a small company from the heart of Europe. We're actually in Austria. So the picture you see on the left side, if you're into snow, hop over, we have a bit of it. We're part of a carrier network, and we act as an innovation hub for our carriers. So whenever they have a task, they are not flexible enough or that they consider too complicated for their default processes, they come up to us and we solve them for us. And of course, since a lot of our carriers are offering telephony services, it was logical that we get into the UC business as well. And we started to develop a UC as a service platform in 2005. So before the whole thing went really off and got hyped, so we've been there for a long, long time. And our platform was initially built on a commercial solution. In 2005, Asterisk was not that good as it is now. There were little options, so we took PBX that was on the market and made it multi-tenant ready with our own business logic and our own solutions. And things were running well for us for decades now. We have a steady growth on the Austrian market, on the limited market of 4,000 to 6,000 endpoints. Everything was good and cozy till 2021 when our main vendor launched a cloud platform of its own and tried to put us out of service. His idea was, you know, your platform is doing good. We take your customers, you can move it to our platform. We stop selling you licenses, we stop selling you support, effectually forcing us out of business or reducing us to the role of resellers. So that's where we were in 2021. And you can imagine we were really shocked and standing with our backs against the walls, facing a tech giant on the market. We weighed up our mind, what can we do? Are we happy with a reseller role? I don't know if you've ever been to Austria, especially to the mountainsides, but once you get up above 3,000 feet above the sea level, people tend to get a little bit stubborn, and so were we. And we decided, no, we don't give in. We are no resellers, we are makers. We want to stay innovative, we want to stay independent, and that's why we decided to reinvent our platform for our customers with a drop-in replacement approach based on open source, based on Asterisk and Kubernetes. So, who are we? My name is Georg Rinnhofer, but you can call me Georg, easier to pronounce in English. I am the head of market for unified communications with WorldDirect.
And my name is Florian Lechner, and I'm the head of technology for the infrastructure in the unified communication part.
And a few more details on the agenda. Today we'd like to cover how we switched from a closed to open source while being in full service. What we learned in the process, what takeaways we had on this path, and we want to emphasize 3 major points. 1, the scaling parts, the benefits for scaling if you use Kubernetes. 2, the problems and issues we had with SIP and RTP routing, things to consider. And the last part is the failover and resilience mechanisms that are provided by Kubernetes. Before we look into the new system, just to differentiate a bit and to better understand why we made certain decisions, look back to the architecture in 2005. It was state-of-the-art in 2005, just a classical architecture. We had our proprietary core service. It was a large multi-cluster solution. The multi-tenancy only was by infusing a logic that we built on top. We had the external licensing that we had to take care of. This shared hardware allowed us very, very good scaling. So our smallest customer started with 5 phones, our largest with 4,000 phones. The core PBX did not provide all the features that we had to offer to our customers on the German and Austrian market. So we had to add other third-party and custom applications. And last but not least, the whole system was managed via an umbrella management. So no technician, no customer, no user ever got in contact with the backend services. All was managed via the umbrella management. This architecture was fine. It was state of the art when we started, but of course it had some shortcomings. One, this custom multi-tenancy on this cluster caused a lot of overhead logic. We had to implement a very, very complex routing logic, which made operational hard for us. It was one large system for everyone, so if the system failed, it failed for all our customers. We had no customer or service level scaling, so if one service or one customer went haywire, it had an impact to all our customers, which happened sometimes and was not so funny. And expansions were really, really hard to do. We had to take a lot of money, buy huge new clusters for maybe one new customer when we reached certain thresholds. And we were bound to special hardware. We will cover this later on when we come to the failover and resilience topic. So in order to maintain a carrier grade system and to meet our service level requirements, we had to invest heavily in underlying hardware. And a commercial part, of course, we had external costs. For licenses, we had the risk of external dependency. As I said in the introduction, the third party wanted to put us out of service. And also the voice endpoints, the phones were limited to some models. To have it a little bit of an overview of the cost structure, so the 2 green slices are the costs we had for external vendors. So a huge part of our platform actually went to an external source. So, and now we come to the new architecture. As I said, the old architecture was not bad, but of course the shortcomings, we wanted to avoid them in the new system. And when we started to think about the new architecture with Asterisk, we also discovered that Kubernetes can help us very much. And our new architecture the first thing we decided is we get rid of the huge monolithic architecture. So we decided to go for separated namespaces. Each customer had a separate namespace. Each customer had pods of their own, classical microservice architecture. And those pods, of course, were resource isolated. We used Kubernetes internal services for load balancing. So we deployed multiple pods, had a service on top of this, and Kubernetes took care that all the pods get addressed. But of course, we had to think about persistency, data persistency, so a persistency layer was introduced as well. As you might already see from this picture, this is a very dynamic setup. So those Kubernetes pods are created in an instant, they get deleted, IP addresses appears, they disappear again, and you need to keep track of the whole changes. So we had to introduce a system that we call dynamic route propagation, where all elements that need to know about Asterisk and routing components are informed about their existence. Then we thought about, okay, is it smart to put everything in a custom namespace? And the answer was no, it was not. So some resources are better to be shared because duplicating also duplicates the resources need. So we introduced a shared area as well. we went for network separation and for protection reasons. So we decided, since we went for a cloud-first architecture, that we only want to expose very, very little IP addresses to the world outside of a Kubernetes cluster, so that we don't need to announce new IP addresses in case of network changes. So we separated the Kubernetes internal network from the external network. This will be important for later on topics. And again, the whole platform was managed by one umbrella management. Nobody got in touch with the containers. Yeah, that was the new architecture. So since we love to have a high blood pressure, we will now see the first live demo.
And I will guide you a little bit through. So Georg will open up our front-end administration for multi-tenant administration and will create a new customer. The only thing we need to add is a name, and after that we can apply it. This will trigger a Helm chart deployment within the Kubernetes cluster, creates the namespace, and sets up a complete custom environment. To illustrate that, we will switch over to another front end. This is not from us. This is Rancher, which is one of the UIs you can use with Kubernetes. You see, we already created a namespace, AstriCon, and a suffix, so that the same name from a customer can be recycled and still be unique. And we should now see the first pods to appear. Most of them should show up right away. The one which takes a bit longer is the Asterisk container, due to the fact that we have a local database in there that needs a little bit to initialize. So I think for a demo, that's how fast you can set up a customer. It takes about 3 minutes from start. Thank you. Let's continue with the presentation. No?
Sorry. Thanks for pointing out.
Sorry. I was only looking at the little screen.
Maybe we should switch places.
Sorry again. We'll have to create another customer. Let's go. Yeah, AstriCon 2025. But it's still the same step. So customer is being created, and we'll switch over to the secondary user interface, which is not from our side, but it's a general one. And here you see the namespace has been created. Now the second one as well. And in the background, the full automated deployment is actually running. We have, as said before, most of the containers or pods are immediately started. The Asterisk one takes a little longer with the database initialization and propagation. But after the 3 minutes, actually the customer can have a fully functional system with a direct inward dialing number and can be used appropriately. So now we switch over to a more technical part. The 3 points we want to look at, which are scaling, SIP routing, and failover and resilience. So you all know the typical usage scenario in a voice system. So you have the core area during the day where you have most of the traffic. This is from 7 in the morning till 7 in the evening for us. By the way, this is our real live data, or real data from our system. And then you see there is little usage in the outside times. For us, that's important from a scaling perspective to also say, okay, we wanted a system where we can reduce resources during the off-peak hours so that we have less cost on it, especially if you have a pay per usage fee for every infrastructure you're using. This really gives you a great benefit. The other part we considered for the scaling part is the bursts in traffic. We wanted to illustrate that a little bit with a very small scenario where you would imagine 4 desk phones, and all of these 4 desk phones monitor all the other 3 phones, exact itself, with a BLF feature. And if you have an incoming call, so you have one call coming in, which then, because we have a broadcast hunt group for, across all 4 phones, it would fork off 4 new calls and would then fork 12 SIP message updates for the BLF part, so a total of 17 SIP messages just to going out for this small setup with 4 phones. In reality, we have these setups with 20, 30 phones, so you really can imagine the burst of traffic on a very short time. The other part, which were important for us from a scaling perspective, as everyone knows, voice traffic is very latency sensitive, and people do not like to wait for ringing, for audio quality. So that was another important part for us. And we have seen by the analysis of our CDRs and usage in the past that we have very, very different usage scenarios based on the customer. We have small customer with a very high call volume, large customer with little volumes, customers who have actually calls 24/7. And we wanted to also accommodate these scenarios with our platform. What we ended up to do, we said, okay, the easiest and most practical one is to use small units of work and go with the scale-out architecture, which works great if you have stateless services, or the services by themselves don't need a high coordination for being high available or a cluster. As well, we integrated a scale-up part into the scaling we undertook, and these were for the services with either high coupling from a cluster perspective and or a rather high base resource consumption, so where it would take a lot of time to start up an additional nodes. Sorry. So in the end, what were the takeaways from looking at the scaling? We were able to achieve some fluid resource consumption and granular scaling on a customer base compared to the very monolithic approach we had in the past. We also can apply a usage profile specific to a customer. We can disable features on a customer individual base. Or add on-demand features to an existing deployment. This allowed us to reduce the cost of operation as well as to get better ESG performance numbers, which is a big part in our industry. And as well, we wanted to give you a little demo. Hopefully this time we are smarter. Showing it on the right screen. We will do a scale out. So we'll just add to the customer we created previously a secondary asterisk because we started out with a single asterisk node, so not a high available solution. And by just clicking the little plus button here, we are adding a secondary pod within the Asterisk service on the platform, and it spins up that as we speak. Again, it takes a little bit for the database synchronization and resynchronization with the secondary node. We will later see that we chose to have a independent database per asterisk, and we take care of the synchronization between these. So we wanted to make sure that call performance works at all times. As soon as this is done, we can then also increase the resources for our asterisk pod, which then will increase the resources on both of the pods underneath the configuration. Yeah. So Georg will go into the configuration editing also here in the UI, and we'll move the RAM up from 786 megabytes, which is like the base we figured out for Asterisk to work properly, to 1 gig. And it's now deploying the resource enhancement from a scale-up perspective. The important part you see here is it first deletes the latest created pod and upgrades the memory on this one. As soon as that is done, it will only then kill the first one. So you can actually do these resource changes in real time while the customer operates the platform. No calls get dropped. You can still continue to use it with no interruption. That was an important part for us to see. Now you see the one got removed and the second one should now cycle through. So we don't want to bore you any further with that, and we'll continue with the presentation. Yes, I'll let George do this. That's his baby.
Yeah, that's my baby. So when we had the scale up and scale out technologies in place, we thought, okay, wouldn't it be cool if we'd have an AI system managing this for us? And of course, no presentation would be cool without AI those days, so we added one here as well. And we invented a method we call, or a service we call hybrid autoscaling for web services. And this service works in a very slick way. Like every other autoscaler, he takes into account very common parameters of the platform, CPU, RAM usage, you name it, but also takes into account some very voice-specific parameters like CDRs, behaviors, and other things. And the idea was, let our pod environments run with a minimum set of resources, so the customer can do basic calls, but that's it. But if there come times of higher traffic, and then we want to be able to automatically scale up those pods and be ready when the customer uses them. And once he's done with his usage, we will scale them down, and thus allows us a very, very efficient use of our resources. We wrote an IEEE paper, the feedback is pending, and the key finding was it works. So we managed to implement it. If you see the bars, the 3 bars on the bottom right, you see on the left an autoscaler that comes with the Kubernetes cluster that is already there. You see on the right autoscaler that is from a different research facility. And in the bar in the middle, you see our autoscaler. We also developed it with a university. So our engineers were working closely with the University of Innsbruck. And the bar indicates the number of dropped calls. And you see, with our autoscaler, even in high traffic environments, it was possible to scale down and scale up automatically when needed without much calls get lost. A little bit to tweak is still there.
So that concludes scaling, and we'll hop over to SIP routing. We had a few challenges, specifically with the edge node of the Kubernetes, that we have only private networking inside. We didn't want to add an additional SBC at that border, so we came up with a little bit of a different approach. As well as what we saw, we have a very dynamic environment where IP addresses, resources change, customers are added, which we want to do without having to restart or disrupt any services. For doing that, we came up with a strategy, what we call liquid SIP routing discovery, which in the end monitors the Kubernetes environment as a single source of truth, which services are running, where are they running, how can they be found. And we tap into the Kubernetes API and then distribute over a message bus these informations to all the components in the SIP signaling way. And we'll go a little bit deeper on how that works. So we saw earlier how to create a customer. When the customer is being created, we via the API, they show up in Kubernetes, and our routing coordinator service actually monitors the Kubernetes API and sees, oh, there's a new asterisk showing up, how to make that available from the PSTN side of things. We distribute via the message bus that information to two components which are part of the SIP routing. One is the routing application service, or RAS, and the other one is the Camellia SIP ingress controller. So we wrote our own ingress controller for Kubernetes, which is specific for SIP and RTP services. And to continue the same thing, so now we have advertised that there is a new customer, which number and so forth, and how to route there. So when an incoming call occurs from the PSTN, the first part is to look up the main number or the direct inward dialing number, and we need to choose the system. So here we have the number lookup. We see that the customer is actually enabled and a valid customer, and we get our Kubernetes namespace, so to know where to drive, and we use the dispatch module on the Camellia to then actually route the traffic to all the possible nodes. The second part is then to say, okay, we need to do the dispatch group lookup to really find which actually physical Kubernetes worker nodes are the ones behind which the PBX is running, and that's the second step. And as soon as that is done, the call can be signaled and works. The other part, which is also part of this liquid dynamic routing, is in the case of a failure or a manual interaction. You see on the right-hand side, we have a list of where to find which customer's asterisk, or one of the cluster nodes, if there are multiple. And imagine that one of the containers would die or would be restarted for whatever reason. Then the next step is to immediately remove that from the dispatch group list. Then the container gets automatically repopulated due to the fact that Kubernetes has been informed that at least 2 need to be running at all times. As soon as that is done, it's get added to the list again, and traffic could flow there as well. Okay, the next part is, now we have looked at the signaling side, is the RTP part. We have most of our customer from the legacy side are all MPLS customers, so with sometimes low bandwidth locations. So we have a direct media first approach, so that we try to connect the phones directly. If they are internet-facing phones, we actually do still work with direct connect, but we use an RTP engine in between for the internet-facing phones to reconnect. But also the connection from the PSTN to that media engine is done with direct media, and there is little to no RTP traffic flowing through Asterisk in our environment. There are, however, some special cases, for instance, early media, where we do send the RTP traffic into the Kubernetes cluster, and I want to show you how that is being achieved. First, we just take a very small or little look at direct media routing. Works great with Asterisk, and there is no issue. We just added a custom attribute which is relevant for us to know that we do not inject the RTP engine on the Kubernetes edge into the SDP messages to not get any confusion. Yeah, and that's our addition. So you see this little attribute. And here we see the early media. This is a rather complex slide. I'm well aware of that. But I think it's an important thing to show how we solved that. So we still want to keep the direct media reinvite valid. So we need to know the original IP addresses of the components from where the signaling side is coming. But we also need to route the traffic through the Asterisk, the Kubernetes edge to the Asterisk to actually have early media flow correctly. So what we decided to do is we added the RTP engine beside the Camelio Casico on the edge of every Kubernetes node. And we'll ask the RTP engine to inject its data into the SDP message, but don't let it do it correctly. We introduced an additional media type block, which we call proxy audio, which we use in the case of early media to actually inject the RTP engine in the SIP or in the RTP traffic. And it flows correctly to Asterisk. Asterisk takes care of the media handling for early media and sends it back. And later, when the call is being picked up and we are in the real call scenario, we have to do a reinvite for the direct media part, and then the original SDP message media block type is being used. So that was a little change within the Asterisk code to achieve that. So in the end, we saw that we needed the RTP proxy. You can use whatever one you want to use for that to support early media and other media parts, also for music on hold. It's an important part. We also looked into the option of using outside media sources for music on hold, and both of them work in our environment. So that concludes SIP routing, and the next part is failover and resilience. So as you heard, we are part of a carrier group, and therefore the expectation for telephony is carrier grade redundancy and resilience. So we are supposed to have 5+9s at all times, and we needed to achieve that also with our class 5 operations. In the past, we had an extremely complex software setup to achieve that, and very high and specific hardware infrastructure. We needed to achieve that availability numbers. We had NetApp Metro cluster cross-region, as well as a lot of network components and VMware cluster with failover parts, as well as a SQL Server enterprise cluster with automated failover. So you can imagine in the end, we paid a lot of licenses and hardware costs. And when we started out the new architecture, we wanted to reduce these external dependencies and cost structures. So our approaches for that were, we wanted to take off-the-shelf standard hardware, which we can achieve still the availability which are required from us. We also saw that the more stateless we can provide our services, the more resilient they become, because we don't have to have very special software for coordination purposes and other. We wanted to make sure that we have a platform which we called self-healing, so with a declarative environment of Kubernetes to auto-repair, auto-redeploy, auto-start elements without any operational interactions. And we wanted to reduce, that was the biggest part, the failure domains. Yeah? We had a very large failure domain, like a central database server, which if that failed, all customers were failing. On the PBX side, if one of the clusters would fail, a lot of customers were impacted, and use as much of the redundancy the platform would provide us with. So this is how we ended up with the new architecture. So we can use off-the-shelf hardware and just have a ton of it. So a failure per se does not have a huge impact. And we also chose to go with a converged infrastructure, so we added storage to all the compute nodes and redistributed the storage across all the worker nodes, so all the data is available on all nodes at all times, and with the help of Kubernetes, the Asterisk instances, for instance, are never run if they're multiple deployed for a customer. They are not running on the same worker, so a complete worker failure has actually no impact on call operations, which is for us the most important part. I also wanted to here look into the changes we made or our thinking about it coming from the old monolithic active-passive cluster world. So you see in this drawing we have two active-passive clusters with registered phones. We have a central database which actually would cause issues for all systems. You see the phones can only register with the vendor phones we have been using and still using to one of the cluster nodes, which is the active one. If that would fail, all the phones have to reboot to re-register. So the customer will see that and it will have an impact on the service. We wanted to reduce that impact for our customers, and so we came up with a different architecture. We put in an individual database per Asterisk node, and have the individual Asterisk node, which can be replicated as a cluster active-active in our scenario across the environment. We have some shared services which are commonly used. And the last part is we added the routing application server, and actually the phones register with that routing application server, which by itself is a multiple cluster VRRP combinations. So for the phone, it looks like a singular IP. Behind there, we have the redundant services, and even if an Asterisk should drop out with the dynamic routing and route propagation, you can still run your calls, and the phones do not have to reboot and re-register at any time. And as always, we'll do a little bit of a demonstration. Again, in this case, we will delete a front-end part and let the system heal itself, and then we'll do the same with an Asterisk node. Unfortunately, we cannot show you that actually the call stays and you can continue to talk because we didn't feel comfortable to bring desk phones along. So we are killing actually a front-end node, in this case manually, and we have to refresh to see, but it was so fast that the front-end container, so the administration interface, is back up again. We just see that it's now running for a few seconds only. And now we do the same with the Asterisk. We'll take one of the two pods, even this case, the oldest running one. We delete it again. We would see that this has no impact on an active call, and also it recovers itself by automatically starting again. Yeah.
And please hands up everyone who has ever deleted an Asterisk of a productive customer in the while used in broad daylight without blinking. So no one. We had to get used to it, but it works on our platform. So
yes, it's a little bit of a change for our operations team to actually fix something by deleting things. Yes, and then we'll continue with the presentation. So what were our takeaway from failure and resilience part? We reduced the failure domains, so some impacts only take one customer. We we're able to actually make everything an active cluster, which was very important for us for availability, not throughput. And we have the complete declarative automated deployment. That's the Helm chart within the Kubernetes cluster for customer environments that is customized to set up actually the Kubernetes cluster in preparation for our services. And we are using Ansible for all the services which are actually still running outside of the Kubernetes cluster. And one little thing we did not mention before is we can actually change the version of a single tenant. Either if you need a hotfix for a customer and or an additional feature which is very specific to a customer, we can deploy it without being worried that we break any other customer's ongoing operations. And that concludes this part.
Thank you. So the bottom line. Asterisk on Kubernetes yields a lot of operational and commercial benefits. For us, it's the right way to do things. It was not easy, but it turned out to be a very good decision. When we started our journey, we had a lot of people telling us, you can do it on Kubernetes, you can do it with Asterisk. How dare you stand up against big tech giants having thousands of engineers? But we showed that it is possible, and it is possible with the help of the open source community, with the help of Asterisk, and we're grateful for your products. Two, if you plan on implementing Asterisk on Kubernetes, be aware of the SIP and RTP routing. There may be different ways to ours to implement those things, but they are tricky. We can give you the advice, think ahead, define your use cases, define them properly. This might save you a lot of headache in the long run. And last but not least, if done consequentially, Asterisk and Kubernetes merge to something new. We sometimes call it Asternetes, because you can't design one thing without thinking of the other. So, yeah, that's it. Thank you for your time, thank you for your attention, and if there are questions, we would be happy to take them.
Oh, yep, got a question right up front here. Here you go.
Hello, great presentation, thank you very much. So my question is, I'm in a currently in learning phase to do something like this. But I choose serverless rather than cubes. Like I said, I'm still exploring things. So what are the reasons you guys to choose Kubernetes, which you need to maintain, other than serverless, which all the infrastructure is maintained by the cloud provider? It's much easier, right? I mean, that's what my thought. So what makes you choose K8 rather than serverless?
That's a good question. There's a very easy answer: regulatory requirements. We are running our own data centers, and the infrastructure is also run. We are not using any cloud services underneath. So we have government customers which fully require that we control the hardware end to end, including network and infrastructure. That's a big part. And we are coming from a very hosted, self-hosted services, so it was part of the decision as well.
Thank you. But you think serverless could be an alternative, right?
You will have a few interesting challenges probably with SIP and RTP, specifically with the network side of things, but I think it's doable, and from an operational side, it could be very interesting.
You won't be able to control the latency, and you have no idea. We have Fargate. We run services in Fargate, and they work media in our Fargate. So it works, but it's it's like you pray, because if something goes wrong with latency, you have nothing. You have no idea. You can't control it. You're depending on the provider. And HTTP world, yeah. In voice world,
It has.
So, a question about are you running, how did you solve you're running Docker, I'm assuming, inside these, right?
It's actually containerd.
Oh, it's containerd.
But
And from the networking point of view, are you doing hosted networking, or are you doing like NAT inside those?
no, we are actually using the native network of Kubernetes, so the CNI part, but it's not hosted host communicated network, so we are not exposing the ports outside. Asterisk is only visible inside the Kubernetes network, and on the network on
So
the
you're
nodes on the
using local IP addresses, and that's why you need RTP
yes.
engine outside.
That is why you saw the very specific SIP and RTP routing and ways we're doing it. What you have to remember, we do sort of have a hosted mode, if you want to call that, with the Kubernetes daemon. Yeah. So on all worker nodes, there runs a Casico and an RTP engine, which we actually use as not really an SBC per se, because there's no call or back-to-back user agent functionality at that end, but that's the termination point for the SIP traffic, signaling traffic, as well as the RTP traffic, and then we layer it inside, and we do a lot of translation and rewriting of the headers and stuff to make it work.
To add on this sounds complicated, and it is to a certain point, but we decided to go down that road to be to have a cloud-first, cloud-native architecture. So we could take our platform, put it somewhere else, have just a few IP addresses pointing outside, and this would be it.
Correct, yeah. And you're running Asterisk with one network interface, right?
Sorry?
One IP, right, per Asterisk?
Yes, we are using a service IP, but on the worker node on the outside, because the Asterisk would do it with the active cluster run on 2 different nodes. So the routing application server actually has the dispatch group, so it with the routing coordinator learns on which nodes it will find the Asterisk services and then talks directly that way. This is also a path optimization from a latency perspective. But if you really want to know the very details, we're glad to share.
So if anyone is interested in more details, we love to talk about our solutions. So please don't be shy, come up to us and we will give you even more insights and can look into the infrastructure. So thank you.
Yeah. Thanks very much, Georg, Florian. Great presentation.